Hey, my name is Csongor and today I will give you a friendly introduction to deep neural networks. Let's start with a question. What is machine learning? Instead of giving you some high-level definition, let me start with an example. Suppose we have a human and we have a cake and we want to make the human to go and get the cake. We do this very simply. Just tell the human to go and grab the cake. Goes and gets the cake. Now, we have the same situation, but now with a robot. It's not that easy anymore. We can't just tell the robot to go and get the cake. We have to give it a set of instructions. So, for example, we could say, turn right, then go 5 steps, then turn left, then go 2 steps, and grab the cake. This seems like an alright solution, but what if the robot would start from a different position? It would not be simple anymore. We would have to give a totally different set of instructions. This is fairly inconvenient, so we want a more general solution. Let's see how can we improve. We could say, for example, to the robot to go and calculate the distance to the cake. Let's say 5. Next, we would tell the robot to move around, pick a direction where the distance decreases. It will try to go this way, 4.2. It will try to go this way, 5.4, and so on. Next, we will tell the robot to take a step in the direction where the distance to the cake decreases. And then it just has to repeat the same process all over again until it finds the cake. And this is in a nutshell what machine learning is. Let's see another example, a more complicated one. Suppose we are on top of the mountain, named Mount Everest, and we have no idea how did we got here. All we know is that we want to descend from the mountain. Moreover, it's foggy, so we can't see too far away, only around us. What do? First of all, we look around us and we see which way to take a step so we can descend most. Let's say this way. We take a step in that way. Now we do the same again. We look around us and see which way we can descend most. Let's say this way. And then again, until we descend the mountain. This algorithm is called gradient descent. And if you like math, what we really did was we looked around us, we took the derivative or the gradient of our height function, and then the gradient pointed at the direction where we decreased most. And then we just took a step in that direction. So let's look at the problems we just solved. First problem, to go and get the cake. Second problem, to descend from the mountain. And now, just think about any problem that you can solve with machine learning. Let's see how did we solve these problems. In the case of cake, we minimized the distance to the cake. In the case of the mountain, we minimized the height. Now, to solve any machine learning problem, what we have to do, first of all, is to devise a metric which will tell us how far we are from the goal, and then we have to try to minimize it. Basically, we want to minimize the error. This is how we solve most problems in machine learning. So, for example, we teach computers how to play Go, how to play Jeopardy, we teach cars how to drive themselves, and many more. The core of all these applications is what we are going to talk about today, neural networks, the basis of deep learning. So, what is the first thing that comes to your mind when you hear the word neural network? I don't know about you, but when I first heard about it, this was the first thing that came to my mind. Luckily, later I started seeing actual neural networks and I realized that they are way more scarier. Something like this. Then, studying them even more, I realized that they are quite friendly, and now I see them something like this. I think of them as a kid playing in the sand, and there are some red and blue starfish. And I tell the kid, alright, could you just draw a line to separate the red from the blue starfish? And that's what neural networks do. You have some data, and you want to tell the computer, hey, can you split the data? It will say, yes, of course, here is the line, or some more complicated solution which will split the data. How does it do this? The same as we solved our problems before, using gradient descent. Let's look at an example. Suppose we have the above set of points, and in the beginning, we just draw a random line. The line says that all the points to the right should be classified as blue, and all the points to the left should be classified as red. Now let's see how well did we do with this line. As you can see, not quite well. We have 3 misclassifications. So we would like to move our line using gradient descent in order to minimize the error. Let's say we move it this way. We still have 1 error. Now we move it more, 0 errors. Perfect solution. Although this seems a plausible one, it still has a problem, which makes it almost impossible to work 2 times. Let's get back to our problems we try to solve. So we try to get the cake, we try to minimize the height from the mountain, and we try to split the data. Can you spot the difference between these 3? Let me tell you. For the first 2, our error measures were continuous functions. The distance to the cake is a continuous number, as well as the decreasing height. What about the last one? It is a discrete function, because the error will always be a discrete number, whether 0, 1, 2, and so on. This leads to the fact that finding the derivative will not help us to descend, because our function is non-continuous. And if you remember, the basis of gradient descent is finding a good derivative. Let me illustrate this problem with a picture. Basically, what I am trying to do now with the current error measure is to use gradient descent from stairs instead of a mountain. So I look around, and if it's foggy, it feels like I'm on a flat land, and I can't really figure out in which direction to descend most. So I get confused. So we need to devise an error function that is continuous. Let's say that instead of predicting whether our points are red or blue, we will change it and we will say we will compute the probability of the point being well classified. We will use a sigmoid function for this. For example, in our case, the function might predict these probabilities. We can clearly see that those points which are well classified have high probability, and those which are not well classified have low probability. Now, if you want to calculate what is the probability of all these points happening in this classification, we just take the product of them. Now let's try to move our line in the better position, where we have all our points well classified. Now, if we want to calculate what is the probability of this interpretation happening, we will get this number. This probability is way higher than the other one. What we did here is called maximum likelihood estimation, and that's how we are going to calculate our error function. So, let's see the 2 pictures from before. As you can see, here we have only multiplications. Question: how do we turn these multiplications into a sum of things? Because, as you remember, we said that an error function is a penalty that we can add up. The answer is, you take the sum of the logarithm of the probabilities. Sounds quite simple, right? What I also did here, I just multiplied by -1 so we can get a positive result. The algorithm which solves the problem this way is called logistic regression. Now let's see what does this have to do with artificial neural networks. Let's try to interpret that line mathematically. That line can be also called decision boundary. And we will say that is 2x plus 3y equals 0. We can represent this as this little node here, where the inputs are x and y. We have the coefficients 2 and 3 and the threshold 0. This is called an artificial neuron because it kind of resembles a biological neuron. Let's see how. So on the left you have the 2 points, 2 coordinates x and y which resemble a point, and the probability of the point being red is calculated and sent as output. Similarly, on the left is a biological neuron which through the dendrites take as input bunch of nervous impulses, adds them up in the nucleus, and then through the axon throws out another nervous impulse. Something like this. Now let's generalize this, and here you can see the first artificial neuron devised in 1943 by scientists McCulloch and Pitts. On the left there are the inputs followed by the weights. These are multiplied and then summed up, which then are pressed to an activation function which performs, in our case, the sigmoid function and outputs a probability. This represents the basis for artificial neural networks, and it was working quite well on data which was linearly separable. This means that there existed a line which separated the data points. Around the 1970s, scientists discovered this lack of the algorithm, that the perceptron is not working on linearly inseparable data. For example, this set of data points. This led to an AI winter of 20 years, when they realized that they can solve this problem by only stacking more artificial neurons together. Let's see an example. Suppose we have one neuron which comes up with a region on the top and the other neuron with a region on the bottom. Somehow we will try to merge them, to lay them on top of each other to get a solution. Then, merging also the decision boundaries, it kind of resembles this. Let's see what really happens here in terms of probabilities. Let's say we choose this point. Then, the probability of that point being blue in the top region is 0.8, while in the bottom one is 0.7. We add this up, pass it to the next region, the combined one, which, using the sigmoid function, will compute a probability of that point being blue with 0.81. Now, what happens if, let's say, you want the upper pattern to weigh more than the one on the bottom? It's simple. We add a weight to it, and now our resulting pattern becomes something more like this. You can also see that we added a coefficient to the last region. We can add coefficients to any regions. In our case, -3 will be just subtracted. Now, let's interpret these into artificial neurons, like we did before. Consider these two functions as interpretations of the decision boundaries. Encoded to neurons, they would look something like this. As you remember, we did it before too. Now, if you want to add the combined layer 2, just remember that the top neuron weighs 7 times more than the bottom one, and then we can come up with something like this. You can see 7 and 1 are weights, coefficients, and -3 is the coefficient of the region. And now the magic happens. We have our first neural network. Cleaning it up a bit, it will look something like this. So we get the inputs on the left, x and y, and then all these coefficients, 7, 5, and so on the right. And on the right we have the output node. So if you have to remember one thing during this presentation, remember this. Whenever you get scared about an artificial neural network like the one on the left, just think about them as a combinations of regions, like the ones on the right. For example, this is the mental picture I have when I see a neural network. I have my input layer, which is the x and y, then the hidden layers, which are the lines used to cut up my final region, and then the output layer, the final region that I obtained as a combination of those linear regions before. From this point, I can play with the number of layers or the number of nodes in layers however I want. The more layers we have, the deeper our network will be. So finally, we are able to understand that scary picture from before. Sometimes this depth of the neural network might not be enough for your solution. No, it's not a problem. You can go deeper, how deep you want. For example, this is Google's Inception v3 architecture, which is used for image recognition. Now, for those of you who are getting hyped about neural networks and you want to train your own, here are some resources. For people who first want to dive into the logic behind neural networks, I would recommend checking out the online resources like Udacity, edX, Coursera. For the more adventurous ones who like to program right away, go and start programming with Python, and then explore one of the libraries like TensorFlow, Keras, Theano, and so on. Thank you for your attention. Please post any questions below and I will try to answer them. See you.